Good morning, everyone. Welcome to a new semester. I am Ranga Setlur. I'm the Associate Director of Community Engagement at the Institute for AI and Data Science here at UB. This Tech Exchange Seminar Series, this is the third semester that we are running it, and it's become very popular. We've had a lot of faculty sign up. One of the advantages of doing this through IAD is that we have a huge affiliate list and the ability to propagate information about all of these activities across the campus. And that way we could hopefully try to get connections between researchers across disciplines. AI is sort of a tool that is now being used across all disciplines, and you need multidisciplinary collaborations to really make an impact in many fields. And so this is a small effort in trying to do that, especially early career faculty. This would be a great opportunity for them to put their research in front of the larger university community, and hopefully connections will be made, and these can lead to larger grants and other fruitful collaborations. So I won't take too much of your time. So today we have, to start off the Fall 2025 Tech Exchange Seminar Series, we have two very interesting talks, and I let the speakers introduce themselves first in the way that they want to introduce themselves, rather than me trying to do that. And again, as you can see, these are from different disciplines that we have speakers here. So they will introduce themselves and they'll present about 25 minutes, and then about 5 minutes for question answers. And after the seminar, you can stick around and chat with them. And then we'll also try to make these talks available online and try to get further engagement happening over the course of the semester. Yep. So without further ado, let me have Prashant introduce himself, and take it away.
Hello, everyone. My name is Prashant Sankaran. I'm an assistant professor. Okay, let me see. Okay, perfect. So I'm an assistant professor in the Industrial and Systems Engineering department, and I'm also affiliated with the IAD and also Collaborative Institute of Multi-Source Information Fusion. So my talk today is on human interpretable evaluations of deep learning models for spatial robustness in computer vision. So the general idea of the talk is, like, you might know there is interpretability, which is very important. But at the same time, like when we talk about interpretability in actually understanding whether these models are robust enough or not. So that's essentially what I'm trying to understand. And like when you test a model, you get some results. Can I even understand those results and actually act on it? How do I make it more interpretable? But at the same time, I want to understand, like, can I introduce theoretical backgrounds, which statistics has a lot of background theoretical underpinnings. We wanted to see if we could use those to actually make sense of those results. So today it's going to be a bit more preliminary study. I'm just going to give you some ideas, but the work is going to be following through, and probably you might be able to read the papers in the future. So this project is actually spawned off from a thesis that I advised in fall of 2024. And I'm also currently working with my PhD student, who is Jason Frites. So a little bit background about where I work and what's my research interests. So I like exploiting the synergies between artificial intelligence and operations research. And also, if you wanted to understand, like, what are the different ways in which we use AI for reasoning under uncertainty. And again, of course, robustness of these AI models, which is very important for the safety critical applications we are using nowadays. And also, we wanted to understand, like, can we use explainable AI more and more, so that these complex models are needed for us, but can we improve or invent better approaches for explaining these models? And these are some of the grants I've worked in the past as a student and also as a current, starting as a faculty, just to show you a few of them. So just a bit background, since I see a diverse audience in my podium now. So deep learning in computer vision, what exactly is this? So you can think about this very little cat and also probably a dog. This very good image of a cat and a dog, it's easy for us to identify. But for computers, it's not as easy. So there was a lot of process that has went into to actually identify these. So a simple common task that we would want to understand is computer vision. There are 4 different tasks, very, very common. Image classification. To understand, given an image, I want to be able to label that image effectively, whether it's a cat, dog, or probably a duck. and image segmentations. Within a given image, I want to understand which portion of it is actually a cat. And image object identification, to actually understand within a given image, there might be a lot of objects. I wanted to be able to classify all those objects together. And facial recognitions, you can think about human facial recognition to understand and also to see if this specific human matches with the name that's been given to that human in some database. So some of the popular architectures we should be aware about is the vision transformer, which has a attention model as a backbone, and the convolution neural network and multi-layer perceptron. So these are kind of the staple diet we are currently using and building on top of it to develop more advanced or complex models. And some of the learning algorithms that's been very popular now is supervised, semi-supervised, few shot, and zero shot learning. So think about supervised learning like you have some teacher giving you a set of labels, and also for those labels, you're able to generate a lot of examples. And along with those labeled examples, you're using to train a model to understand how to label new unseen images. And self-supervised learning, you do not have a lot of labels, but you wanted to use some of the labels to extend on top of all those labels. And few shot and zero shot are a bit more interesting. Few shot in the sense that you just use a pre-trained model to detect on new unlabeled data sets, which is very important and interesting because you can think about labeling these information is very, very time consuming and is labor intensive. So we wanted to automate the process as much as possible. And these last two things that you're seeing is actually in this direction. And how do we even evaluate these models? These models are good. Now we want to understand which model is better. So this is kind of a chart that I always present in my class. So because like you might just hear about attention or like any model that you have, you just wanted to compare that model with respect to accuracy. That's the first thing everyone compares against. But there's actually a set of statistically driven approaches that's been reported in the literature. And we wanted to use some of these approaches to actually make sense. So this is one of the things I always present in my class and ask my students to use one of the pathways in this specific chart to actually report the results. So you can start with, let's say, the multi-class classification. That's the most common one that we see. So we wanted for that class, we wanted to see the coherence K or the kappa. So it essentially says that when you have multiple different classes, how do you say that whether a given image will belong to a given class? And if there is any conflict, how do you overcome that conflict? So you can use coherence K to actually understand that or iterate reliability. So when we do the evaluation of these metrics, there could be several tests that could be possible. So some of the tests, as you can follow the chain, you can see like when you have two different models you want to test against them, then you can also use the Wilcoxon sign test. So these are all statistically driven tests that helps you to actually or objectively provide saying whether model A is better than model B. Now, coming back to the performance of these models, these are all good. This accuracy and other things are always there. And on top of it, we need to also perform these things. So it provides us a good measure of how well the model is performing. But on top of that, is it sufficient? The question most of the times is not, right? So I wanted to provide you two different motivations. Why should we care about more than accuracy? So the first one is pervasive use of deep learning approaches. Two examples I'm going to provide, the autonomous vehicles and Amazon Go. Both these examples are very popular. The Tesla vehicle and also the Amazon Go. We all know how it went because although they implemented in large scale, but there was a lot of problems that we were able to identify after the implementation, not before. Because you can think about the evaluation of these systems is complex to start with. And just having an accuracy of these models, let's say 98%, 99% accuracy, is not enough because the test data set is not infinite. It is very limited. So on a very small limited data set, and if you are able to say it's accurate, it's not going to be good enough for real world implementation of these systems in a reliable setting. And the grocery shop, as you know, just go to a shop, take some items, and then just walk off. And everything is going to be built onto your account automatically. But these are all run by a lot of cameras. The infrastructure is huge. And depending on infrastructures, probably the different lighting conditions that you wanted to be able to address, and also what kinds of sensors you're using. What happens to these sensors? You need to keep on maintaining these sensors. So there's a lot of underlying technology that you need to have, and you need to test those technologies. So that's another challenge that we are currently understanding. And also you can see, but this is not stopping. Industry is still wanting to use these technology as much as possible to improve efficiency and get more profits. So it's going to increase, but as academicians and also as responsible AI developers, we want to be able to understand, like, can we improve the reliability of these systems through some advanced methods? So in that vein, I'm kind of seeing there's a lot of opportunities that comes up. And also you can think about we need to vet these process using robust evaluation mechanisms. So what are those robust mechanisms we'll be seeing soon? So just to give more background into what robustness even in the first place is. So think about, I have an image of this dog, and I kind of add all possible variations of this. When I say variations, perturbations. So this is an image. I can actually decrease the gain on this image so that it has different intensity, or probably the lighting effects could be changed somehow. And I would add some blur effect where it's very difficult for me to understand it's actually a dog, but it is a dog. For us, it's easy for us to spot, but probably for a machine, it might not be as easy. And think about rotating it and changing its background color and everything else. The object is not changing. The only thing which is changing is how it looks in that image. We as humans are able to spot exactly this is a dog. Machines might not be able to do it. So we feed in all possible variations of the single given image inside a neural network model. And is it still able to predict if it's a dog? Then it's a good job. But what you notice is like there could be a ton of possibilities, ton of variations that could happen. So that's the key challenge. How do you generate all possible variations as well? It is very difficult. So when you think about the definition, the core definition, so what we see from the literature is robustness is defined as the relative stability of a robustness target with respect to specific intervention on a modifier. So, and this is actually my version of it. So if you think about a deep learning model, I see robustness as being if you perturb it as much as possible, but still the model is invariant to whatever classification it has given. Or probably like it's not changing, unless you change the objective identity of it, probably like if you replace this cat with a dog, it should not change. If it's a cat, it should be a cat, no matter what kind of deformations you perform. And still the object identity is retained. Okay, so how do we even analyze this? One of the method that most of the literature is currently relying on is the robustness. And I wanted to provide you a small view of what exactly the robustness spectrum is all about. So think about the average case. Most of us, we know, like we have a test data set. Within the test data set, there might be a few variations of a single image. Probably different images are provided. And different images with slight variations that you could capture. Probably there's a blur effect that's been added to some of the images and probably some other effect. All these, at best, will offer you an average case of understanding like how best you could have. Because all those images will have some deformities in nature. We're just using naturally collected samples to actually find the best possible case. So this you could consider as like injecting a very small noise into this case, or probably like a Gaussian noise, or any other noise that's been injected into the perturbation set is what you can consider as the average case. The adversarial case, which is very, very important, and a lot of people are currently working on that space, is essentially like, how do I modify a given image in a very small way as possible so that I can fool a given model? That's very popular now. And a lot of attention has been given to the adversarial case. But although it's important, agreed, if that happens, it's catastrophic. But how likely it is to happen? That's very difficult, right? Not as likely as you think, unless like I go inside a sensor, I modify that sensor to actually attack. People might go through all those lenses. But majority of those applications, if you look into, the reliability lies in somewhere in between, the intermediate region. So we want to be able to understand, is there a space of perturbation sets? Within that space of perturbation sets, I wanted to be able to understand whether the model is robust enough or not for every reliable application. Not only worry about the extreme cases, because if you only worry about the extreme cases, everyone is flawed. Every model might be flawed. But how to make sure the reliability exists in that intermediate space? So that was the whole idea behind the intermediate robustness. And at least the robustness is when we measure these robustness with respect to a loss function. So the general idea is you might have this perturbation set, which could be differentiable in nature and also non-differentiable. So think about injecting a noise into an image. When it's a Gaussian noise, it might be integrable, or sorry, it could be differentiable. But whereas when you have these perturbations like translations, when you have skewness or probably scaling them down and up, so those things could be non-differentiable in nature, or spatial perturbations that we talk about. So that is essentially the current talk's focus when you think about these perturbations, which are more natural occurring. Think about you're taking an image. Our hands shake a lot, although there is a sensor which kind of making sure that the shake is not being so prominent, but still the images might go blurred, right? when different people take those same images, you might have different viewpoints of the same subject. So all those things would cause more variations. And all those variations could be non-differentiable in nature too. So we want to capture that space. So here what you're trying to see is essentially a loss function. So when you add a perturbation to this loss function, and you're computing the loss on the perturbed sample, and over a set of all possible perturbations set, you're computing the expectation on it. And the expectation on that over the entire data set is essentially giving you the robustness measure. The same thing happens with the extreme case, whereas instead of using expectation over all possible perturbations, you're using the maximization. So think about this as an L1 norm, or probably, and the other extreme is actually the L infinity norm. So that's what you're trying to compare or compute on top of these sets. So the perturbation sets. So this is broadly, you can focus into random perturbations, adversarial perturbations, and also natural perturbations. So within some of the categories of natural perturbations, you might find an adversarial case. But whereas adversarial perturbations essentially just target optimizing for just one small attack, which makes sure that small changes in the image, not too much small, too large, small changes in this image is able to attack your system. That's the focus of adversarial. But whereas in natural perturbations, these are naturally occurring. Like humans might be able to produce it, or probably because of natural causes. And random perturbations could just be injecting random noise into it. A lot of distributions are there, just sample them and then apply them. So, and getting more into the focus of this talk, which was the spatial perturbations, there are 3 different types of spatial perturbations that you could generate. And a lot of research has been happening in this space now. So think about geometric transformations, which is the focus of this talk as well. So rotation, translation, scaling, shearing, and affine transformations. So these are some of the ways in which you can generate those artificial things, which are very similar to what might happen in real life too. And if you want to go a bit further, there's actually flow-based transformations. So think about a camera and how the movements of those camera might happen. So you can use an optical focus or optical models or optical flow field models, which actually would generate those kinds of disturbance that you would want to see in real life too. And the last one is like semantic spatial changes. So instead of just changing how the image looks, can I change the background on the image and then see if it still works? Like everything is the same, the object itself is not changing, but just change the background, keep changing the background and see if it's going to be any impact or not. So those are some of the ways in which people have addressed the spatial perturbation space. And in this talk, I'm going to focus on the geometric transformations. And in this, what kind of evaluation techniques that I can have for the robustness of spatial perturbation, some related work I wanted to present. And there are 3 prominent works that I was able to point out. One is like the naive approach that you could think about, or actually not as naive as we think about, is like creating a data set, a fixed data set of all possible perturbations that you would want to capture. When I say all possible, probably like rotation, I can have a set of examples that are catering to rotation. And I have a set of examples that are catering to probably translation, and so on and so forth. You can have a very fixed set of database and then compare all possible models to see how well they perform on this new test data set. And they also introduce a new set of metrics, which kind of understands like how well the model performs, adjusted to AlexNet or some other network, which also has like different classes might have different difficulties. So you wanted to cater to those difficulties using that. So they are able to provide that kind of a measure. And what happens is that measure is again going to be related to the accuracy or the error rate, which might not be as perceptive of giving a mathematically strong opinion behind like how well this model is going to do on a very large set. So in that direction, which provides a more interesting take, is the intermediate Q norm measure. So the norm measure is essentially trying to say that over a given input space, I'm able to represent the error as a norm function on that space, on the loss function. So when I'm able to do that, what I'm able to see is how bad it can get, meaning like some of the examples might be really good and some of the examples might be really bad. As I increase the Q value, which is the norm value, I'll be able to highlight those norm or probably those examples which are really bad, highlight those examples which are really bad. So you can think about Q norm as a way of going from the average case when I consider all those examples of perturbations and how the model performs equally to a scale which is infinity norm, where I look for only things which are really bad. So I can go from the entire scale of using just the Q values. So this provides a more robust way for understanding both extremes, the average and also the adversarial case, and also the intermediate case, probably in between all those values that you want to have. So the last one is the Veribus, which I think so is a bit more important because it kind of focuses on how the autonomous driving vehicles are being tested in some of the cases they presented in this. So they have a very specific way of coming up with saying that instead of just measuring, I want to measure violations. So like how many images the network has incorrectly predicted. So I wanted to say that it violated this specific perturbation. So you can throw a lot of examples into it and it was able to detect it. But one of the problems again is like these violations, it's very, very difficult for us to understand. Probably like we could say like it had 100 violations, but it all depends on the number of data points that you evaluated. So here you could see this measure is a bit more comprehensive measure because I can use it to give a very large set. And on top of this set, I'm able to get a very statistical measure, which is theoretically driven. But whereas here, these two methods are human-based or heuristic approaches that's been developed, which might not have theoretical background, but at the same time, it provides some way of actually measuring robustness, which was not present before. So based on those, what were the gaps in these three literature or probably in the past that we have seen? So robustness evaluation, what you could think is also very expensive. So think about you have this test data set of probably 10,000 examples. Of all the 10,000 examples in this test data set, for each example, I need to compute all possible permutation or all possible variants on top of it. Probably perturbations I need to have. Even if you have like 4 different perturbations, that's 4 times the number of, and not just that, within each perturbation type, let's say a rotation, you might have a specific specifications. Probably let's say 30 degrees is what the maximum rotation I want to have in all the perturbations I create. So 0 to 30 degrees is the variation limit, and then all the other dimensions. So it grows really fast. You can think about like 10 times 10 times 10. So just like 1,000, let's just think about 3 different perturbation types. So we have 1,000 different combinations that we want to try for every example. So 1,000 times 10,000 is what you will end up having to compute. You need to generate the data set first before actually evaluating them. So this grows really fast. And if you want to be able to understand robustness, it gets very challenging. And also, after doing all this work, we are not able to understand like how to fix our model. So let's say you just test the model against rotation and you just test against probably translation independently. And now you wanted to see like what happens if the rotation and translation is actually going to impact or not, or probably just what is the effect of specific thing. You can combine all of them and then do a power set. Probably it's a full factorial experimentation you need to run. That could be expensive as well. And the number of examples you need to generate is really large. So, and after doing all this, that although will provide you the interpretability of the entire set, but the number of examples that you need to generate is insanely high. And we do not want to do that. But also the last one, which is kind of when you have the lower order effects, some of the methods so far being addressed in the literature, they either only focus on the lower order effects, probably just translation and rotation separately, not joint effect of both. Or whenever they do the joint effect, they'll not be able to isolate the effect of what happens to the lower order effects. So that's been the case that we have observed in the literature. So what do we propose? So we extend the work first to start with how do we actually define as a norm, but we do not stop there. We define the norm on the spatial perturbation space, but at the same time, we add 2 different things. One is like we define a function called as d-robustness, and we do not assume that the perturbations that you're trying to add are just injected inside these models. We are considering them, the image itself is passed as an input to a function, a complex function that could give any possible perturbation. So that's the first thing we did. And also we are assuming, we do not have any strong assumptions on the d-robustness function itself, but there are certain assumptions. The only assumption we want to hold is like it needs to be integrable on the perturbation set that we are determining. So a general background of what I just mentioned. So this integral is essentially saying that when I wanted to compute the lower norm space, when you think about norm space, think about a vector. There are a set of examples. That all these examples I'm going to pass inside set of examples of input, pass into a model, get an output. Now, if I'm just computing L1 norm, probably I just wanted to compute like how many of those instances are bad. But when I keep on increasing the number of instances, or probably number of the Q value, the norm is increasing. In higher dimensional spaces, I'll try to pick some of the bad instances, highlight those bad instances really large, and kind of like let go of things which are not as worse. So I wanted to spot the bad actors and kind of let go of the normal ones. So that's essentially a way of scanning in this space. So, but I'm kind of doing it only for one given Q values. So I needed to compute this for multiple different values of Q so that I can actually present how the curve is. Meaning, like, if I increase the Q value, is it kind of tapering off, or is it getting constant to a specific threshold, or it just keep on increasing? When it's keep on increasing, it means like it's not robust enough. And it's kind of going to a point where it is stabilizing, then we know that yes, the model is stabilizing and it is robust enough. And you want that curve to be as flat as possible and as low as possible. So that's essentially what we would look for in these kinds of methodology. And there's a lot of theoretical development that we have to do and we have done to establish, like, how do we go about doing it? Okay, but there is one problem with this. So you see this function f of w, this is a high dimensional probability density function. What do I mean by that? So when I was talking about different perturbation types, this assumes that all of those perturbations are joint distribution. So it's a single distribution. Within that single distribution, I can sample at different spaces and then kind of get it. The problem with this sampling approach is like identifiability issue. I'll not be able to understand whether when I sample from this high dimensional space, which low dimensional space is also contributing towards this loss I'm seeing, or probably the problems I'm seeing in this, or the robustness. The loss in robustness I'm seeing, where is it coming from? So it's not interpretable for humans to say, okay, fine, give me 3 things I need to address in this model, so that, like, if I fix those 3 things, I could see some impact in my robustness measure, instead of just addressing everything. So that's essentially the idea for it. Why not decompose this high dimensional probability density function into the power set? So when we decompose this power set, the integrability will not hold, because it's not possible for us to integrate all these areas or all these probability density functions and then compose it back. So what we do, we introduce the epsilon ball idea. What if we consider an epsilon ball that's part of every subspace, except for the large one where we have to delete it? So this essentially will provide us a way of saying that all of them are in high dimensional space too. But whereas for all the low dimensional space that you're looking into, the higher dimensional components are not contributing as much as what you want. It's a very small value, epsilon, so that it makes the integrability assumptions hold, but at the same time, we are able to add all the components back to get the robustness score, which works. So that's the core idea behind it. And although I'm not presenting any of the theoretical results here, but the paper would actually lead on to that. So some of the preliminary results I wanted to share, just to make sure that it's well motivated. The preliminary results on the toy example case is, like, we took a very simple model, CNN model, 3D convolution layer. We have 3 convolution layers, and then we had 1 FC layer to get an output. And we trained this model on CFAR 10. It was a very quick test that we tried to do to understand whether this entire concept works. And we used 4 different perturbation types, which is Gaussian blur, rotation, scaling, scale X, and scale Y. So these 4 things you can think about, although I'm presenting as independently, it's a high dimensional probability density function, meaning like it's a joint probability density function that's been described using these independent perturbation types. And the sampling approach we use is actually the power set decomposition sampling. So when we are able to decompose this into power set, so we can sample across all these subspaces independently. And on top of it, we are able to identify a very smart way of actually navigating these like large spaces by reducing the number of samples we want to take by using the error bounds that we want to hit in all those subspaces. So if you know the error bounds that you want to hit in these subspaces, you could navigate the high dimensional space a bit more like easily. And in order to compute the estimates, we use 30 burn-in samples. So just to give you a brief overview of how the metrics look, let's say this is the test accuracy and this is the loss accuracy. So the intermediate Q robustness value, it comes out to be 5.8. So now what should I do with this? I don't know much about it, right? So the estimate, and also it provides an estimate based on our sampling approach. it gives within 0.03 of the true metric, and the perturbations are significant with respect to the p-value. So all these information is provided as part of the algorithm output. So the good thing, or the main crux of it, is actually the explainability of it. Okay. So what happens is, now I get this kind of a graph, which it's not a neural network, although it looks like it, but this is actually a tree which provides me the high dimensional space. If you remember, 0, 1, 2, 3 is essentially just the different types of perturbation types I was talking about. For all these perturbation types, I wanted to see, with relation to those perturbation types, how the lower dimensional perturbations are interacting or probably providing meaningful ways. So here, the red ones are those significant values or the significant perturbation types that you need to focus on. If you're able to address them, then you can actually improve your robustness. And once you have finished all the red ones, then you can focus on the black ones. And the gray ones are insignificant, meaning like addressing them will not change much. You just need to improve your accuracy of the model, but you cannot actually do anything about robustness of it. So just by this figure, I'm able to debug my model effectively. That's the whole idea behind it. You don't even need to know what happens underneath it. But underneath it, there's actually hypothesis tests happening. So from the higher orders to the lower orders, all there just represents the statistical test that's been performed to evaluate whether the combination or probably the independents are contributing more towards the observed robustness loss that you have. So that's essentially the overall talk. So just to give you a quick takeaway, is like intermediate Q robustness measure can effectively be decomposed using the proposed power set sampling technique. And also this is human interpretable, and we can use it to aid for debugging. So with that, I close my talk, and thank you everyone for coming and listening in. And I'm open to new collaborations if you have any thoughts on it. Thank you.
Maybe time for one quick question while we transition. You want to get the other slide deck? Any questions, anyone? Yeah.
Use one of the mics to answer questions.
Yeah, in the high dimensional set which you mentioned, so you only have the perturbations like a fixed magnitude perturbations in that, because the graph which you showed has like 0 for Gaussian. So the magnitude is also part of that high dimension.
Yes.
Okay.
So you essentially wanted to create a partition product.
Do I need to keep pushing it?
So when you have that assumption, and you want to decompose it further, the range of values within each of those dimensions, the lower order dimensions that you have, is still the same.
Okay.
The only thing you wanted to see is like you don't have a lower dimension getting added to a higher dimension. The integration would not work. So in order to do that, what we want to do is like, why not consider an epsilon bond, a very small perturbation, is very similar to what a average case might look like. So you want to consider those epsilon balls tied to all those lower dimensions. Meaning like all those lower dimensions are also represented in the higher dimensions.
Okay.
In that case.
Right.
And then kind of work the math to make sure that when you stitch all of this together, the error is not as bad as what you want to start with. And at the end of the day, you think about it, although we are able to do integration for this high dimensional space, we never actually integrate anything. We actually sample. Sampling approach is what we use to actually represent that integration or approximate that integration. So when we are doing that, we can actually use a sampling approach that kind of controls for the error that you might have, if at all you did not actually like break everything into some subcomponents. So that's essentially what we do.
Got it. Yeah. Thank you.
We'll take further questions after at the end of the session. So thanks, Prashant, again. So yeah. All right. So our next speaker is Jiayu Peng, and why don't you take it away?
All right. I hope you can hear me. The mic is working fine. Okay, I'll maybe put it higher. So, right. Thank you very much for being here. So my name is Jiayu Peng. I'm a professor in the Material Science Department of Material Design Innovation. Excited to be here, particularly with Prashant. We're actually in the same building, same floor, our offices in Bell Hall. So excited to be here to give you a little bit about what we what we're doing in the lab. So I just started my group about 8 months ago, and my first cohort student just arrived, PhD students just a few weeks ago. So actually, a lot of work I presented here actually done before I started my positions here at UB. But also to give you a little bit of a flavor of what we do and what's coming next. So I will really talk about, I'm a material scientist by training, so we design material, we put atoms together, experimentally or computationally, we're trying to, explore their properties for a variety of applications. That's why we particularly focus on how do we really bridge a traditional physical form approach with more of a data-driven approach that is using high-throughput simulation as well as machine learning. So, what we do a lot, essentially, we, design material, as I mentioned, we, put atoms together in different ways, they have different properties. And a lot of things we care about, for example, we care about material and surfaces that are really important for many applications. For example, they can drive important chemical reactions to convert molecule to important fuel and chemicals. They can really matter, in how do we really, transform and how do we decarbonize or electrify different industry sectors. For example, how do we really, have greener ways of making materials and making chemicals in the material manufacturing and chemical industry on the left, as well as how do we, for example, produce green fuels to power airplanes for aviation or also for transportation by electric vehicles. And a lot of the challenge are really centered on the atomic level, on the material level. How do we, discover the best combination of material in terms of chemical element, or how do we put them together to have, fast reaction rate for different reactions? That's really require, input and a collective work together across different domains of material scientists, also engineers, researchers in physics and chemistry, particularly, we do experiments, we make the material, test the material. At the same time, we also do a lot of simulations to accelerate our pace of exploration. And this is really where ML can come in, AI can come in to largely augment the space we can explore and also do it faster in what we cannot achieve in the past before the current involvement of the driven approaches. And particularly if you think about how do we design material in traditional ways, right? For example, we usually move through what's shown on the left, more of a human-centered approach. Let's say we select a type of material, let's say a number of chemical elements, maybe different, structure prototypes. There are potentially, like tens of thousands of opportunities. We just make them, maybe make a few of them each time. We test them, and then we use our intuition to discover what the next material can be explored to make and test or compute. You can think about from this diagram over here, right? So for example, X, Y axis are just the parameter of the structure of material. Usually we started with randomly sampling the space, and the darker color meaning higher the performance. So we use our intuition maybe to sample a few, and we started using our heuristics to select what's the next one to explore. So you use more of a try and error based approach, and based on our intuition, all the throughput is pretty slow, which means we can only explore a few each time. That's why all the arrows here are relatively thin. And this is, where the data-driven approach can come in, essentially make the arrow thicker, meaning we can, explore much wider, larger numbers of material each time in this cycle. Also, potentially we can have more guided search that, we don't need to sample, the entire space extensively, but we can really focus on the areas of high performance to have a more of a self-driving approach that, approaching the maximum through more of a data-driven optimization path. And so this is really one of the philosophy of what we're trying to do over here. And also, this is also talking about the problems about, like, for example, what is the space we can explore, right? So for the traditional material science group that does experiments, maybe they can make, like, for very hardworking students, maybe they can make potentially a few material per day, in a furnace, and they can test them using different technique in the lab. So on the course of, let's say, 3 months, maybe they can make and test on a scale of hundreds of material if they're really, really very, very hardworking. And now, we have methods of doing computer simulations of material based on quantum mechanics, based on Schrodinger equations. And this is what we call density functional theory simulations. They are really expensive equations to solve. So, even with all the tools that right now we have to automate those type of calculation, generally it takes days or weeks to compute one material because they don't really perform even well from like supercomputers. So over a course of very, let's say 6 months or 3 months of very hardworking students with all the compute, all the CPU and GPUs we potentially we can have, let's say, tens of thousands of material being computed about their structure, their energy, and their property, which is still relatively small. And this is really where ML and AI can come in. We can train surrogate models that potentially that are hopefully as accurate as the 1, 2 tiers on the bottom, but also looking at a much larger space on scales of billions or even more, but also at a throughput potentially making predictions after model is being properly trained on a scale of, let's say, hours or minutes per material structures. And so this is really kind of exciting diagram, but also we want to be cautious, right? So we want to make sure that this really makes sense over here. And particularly, as a material scientist, so we have a different degree of freedom to design material. For example, 1 degree of freedom is what we call compositions on the top. Essentially, we have the periodic table, which elements, how many elements, and what's the combination of them we select from the periodic table. Let's say we can select, let's say, 5 elements, maybe like iron, nickel, cobalt, copper, and let's say platinum, 5 elements. And also, even after selecting those 5 elements, or maybe multiple elements, how do we really, let's say, because essentially the materials, essentially they are piled in crystal structures, how do we really organize them into the same crystal structure? There are really also a degree of freedom of atomic arrangement, atomic ordering, and if we really multiply at least this 2 degrees of freedom, there essentially can be zillions of possibilities. So that's why it's exciting from the left to go to the right, but we also want to make sure and be rigorous. Can everything from the left can go to everything on the right? And over the past century, experimentalists have demonstrated mostly, let's say, what we put in chemical elements, they will show up in the material that we make experimentally. And same for this good way of characterizing ordering relatively well experimentally. And so it's relatively well benchmarked. And similarly for simulations by quantum mechanics, by DFT. But with the new exciting advancement of AI for material, AI for chemistry over the past 5 years, over the past decade at most. So we still don't know can everything on the left can really capture everything on the degrees of freedom on the right. Particularly, a large degree of freedom has been overlooked so far. It's really on the topic of atomic orderings. And I will show you a few slides about how do we study that problem. Can really state-of-the-art machine learning models for material, can they really capture composition and ordering material simultaneously and equally accurately? And this is a really important problem. I'll give you one example. The neglect of ordering can cause big problems. Also maybe debate across different disciplines, right? So if you think about, different atomic ordering, essentially the brown and also the green are different chemical elements. There are different ways of, putting them in the lattice. They can just be like alternating in a very well ordered structures over here, right? So it has nice orders of distribution of colors. But they can also be random, meaning it's disordered, particularly if there's no specific pattern, like how the red and how the brown and green are distributed in the pictures over here. And so in reality material can be ordered, can be disordered experimentally in reality, but a lot of time if we neglect this possibility, it can cause big problem. And one of exciting work, this is actually exciting work from Google DeepMind. At the end of 2023, scientists at Google, they really built a really powerful deep learning model to predict energy of the material based on crystal structure. If you think about the material, the lower energy it is, potentially the more likely you can really make it, right? So that's why they have a really good model. There's no problem with that. But at the same time, Google is making a news article, announcement saying Google, they built this very powerful deep learning model, and then they claim they discovered essentially tens of thousands or millions of new material that material scientists can now discover, haven't discovered over the past 100 years. This is a very, very bold statement, as you can see. It's really causing the sharp eyes of material scientists to really examine this claimed list of discovery by Google DeepMind, and to a very prominent material scientists at UC Santa Barbara. They really sample the 100 material Google has claimed discovered from their list, and they found actually they have already been discovered, which is not really what Google is claiming. And the problem is that actually Google is only computing ordered material structures. So they thought that they discovered new material, but actually the same compositions of chemical elements has already been found experimentally tens of years ago. But the one has been found, also archived and stored in experimental database, essentially are disordered structures. So, without, considering this already existing, already discovered disorder structure experimentally over the many decades ago. Actually, you can potentially make a not very rigorous statement about, you find new material through this very awesome AI approach. And this is really just giving a little bit of cautions about it's important to think about the problems of ordering and disorder structures in material science, particularly in AI-driven material discovery. And so one thing we did in the beginning is essentially we're largely training ML models, on data, from experiment or from, let's say, a DFT computation by quantum mechanics. So one thing we want to make sure is that the data we give to the models are essentially good, right? For example, if we give the models of, let's say, calculations by quantum mechanics, we want to make sure those data provided can really reflect the experimental ground truth. So without even involving any deep learning model, we did a little preliminary works to check the data fidelity. And we kind of explore material, what we call perovskite oxide, that really have the compositions of A, B, O3, which we have two different types of B atoms, they're different chemical elements. That's why they're showing by brown and green colors over here. If you think about, these very simple structures, so there are many different ways to organize them in the lattice in terms of atomic ordering of the same composition. There are essentially 6 different symmetrically inequivalent ways. We can give different names to it. And that's why we really dig through the literature. Has been measured by experiments. We kind of found there's around 200 chemistry has been discovered and later experimentally quantified for their ordering. That's why we just do calculations by quantum mechanics, by DFT, trying to make sure the data actually working fine relative to experimental ground truth. So this is a relatively busy figure, so it doesn't contain ML yet, so I just go relatively fast about it. So the x-axis essentially different, combination of chemical elements, the compositions. And there are many, many columns in these very busy figures, and each column corresponding to, for that combination of chemical elements, exploring literature experimentally, what is the relative energy difference between these 6 different types of ordering of the same combination of chemical elements. So if you think about, just from what you learn, potentially from thermodynamics or statistical mechanics, right? So if this red one, it is much lower in energy than the other ones, which means for the materials on the left, potentially the Roxel ordering has much, much lower energy than the other one. That's why it's more in the bottom. Potentially they are more ordered from pure physics, thermodynamics. And if you go to material on the right, even the red one might be the lowest, but if they're relatively similar energies, which means if all these different ordering can have very similar energies, likely maybe they will form having similar type of likelihood. Thermodynamically, it's potentially more disordered. Actually, this is largely true. It's really giving us confidence the data is working fine. So by the energy computed by DFT or by quantum mechanics, like if you do just a very simple classification model, it's only one-dimensional, linear. So just if it's larger, it's A. If it's smaller, it's B. It's very, very simple classification. Overall, it's working very fine. Like for the prediction by quantum mechanics to the experimental, let's say, measured orderings in the literature. And so this is really, giving us power, empower us looking at very more exciting problems that can the current ML model capturing this ordering dependent DFT energies of different ordering of the same composition that are, because, this is still pretty expensive. As mentioned, it can only maybe takes days or weeks to even compute one material. That's why we want to have ML models to augment the speed. We can make predictions on the scales of minutes or hours. So particularly, for material science and also for chemistries, one of the state-of-the-art material or model class that we're looking at is essentially graph neural networks that really build on the way we can really represent material structure as graphs, right? If you think about the atom, they're really the node of the graph, and the chemical bond or the interaction between atoms is really the edge of the graph. That we can really use, material parameters of the atom. For example, what is its place in periodic table, the row, the column, the atomic number, or other properties of the atom to have an embedding that's initially embedding for different atoms or different nodes that can really add information of nearby atom and chemical bond to each atom just to this very classical process of message passing and graph convolution. And particularly in terms of material structures, it really gives the possibility of, for each atom, for example, this blue one, now it learns a little bit about not only itself is blue, but also it has neighbors that are essentially red and also yellow. That's why, I'm just having a little bit yellowish or orangish color over here, schematically speaking. So through this process of message passing convolution, essentially, each atom learns a little bit about what we call chemical coordination environment. What is the atom surrounding So that's why, this is essentially how, material atoms interact with each other, essentially have different properties. They kind of have a natural way of learning such environment that really give rise to different properties. And then we have further pass it along just to traditional, like how do we do in GNNs, more of a fully connected layer in the end to really predict property P over here. And particularly in terms of ordering, actually, I mentioned they have different symmetries. So we really need to have models that can differentiate or learn symmetries differently. And particularly for the areas of computer science or mathematics, this is really a kind of a hot topic these days in the topics of Euclidean symmetry and equivariance in ML. So, in more of a CES language over here, you can think about if you have a mathematical object, like a graph over here, you can do different symmetry operations to it, particularly with the matrix R over here, if the embedding learned by the model essentially is unchanged, regardless of the symmetry operation in the E3, three-dimensional Euclidean space. We call this model E3 invariant. And if we do the same symmetry operation for the object, if essentially the embeddings learned by the model will also transform in this space accordingly to the same symmetry operation we apply. We call this model E3 equivariant, and particularly we call this embedding a geometric tensor. So it's not just a regular tensor we have in PyTorch or deep learning, we call it geometric tensor because it has the property of E3 equivariant transformations for both the embedding and also for its corresponding mathematical object over here. So this is a relatively computer science language. I think may be the language of many people over here. But what's the language? How do we transform this really to a topic of material or molecule in chemistry or in material science, right? So as a maybe approximation, you can really think about symmetry invariant models. It learns the coordination environment as scalars. For example, for the central gray atom over here, it's really learning its coordination environments, right? So you can learn all the information that can really be shown as scalars. For example, what is the type of element nearby? The type, essentially, there's green nearby, there's brown nearby, and what's the distance? What's the bound length? They can only be shown as scalars. If we move to more of a symmetry equivariant model, essentially you can really learn it as beyond scalar, like vectors or higher order tensors, like particularly in the forms of geometric tensors. You can learn about not only the length of the chemical bound distance, but also the directions, right? So in directions, we really need to use beyond scalar to represent it, and so they can really capture much more information over here. And actually, I will show they have very drastic difference for different type of models about learning the ordering properties. And particularly, we kind of test with different type of flavor of invariant and equivariant models, and we really build a data set about on the scale of 10,000s or even more material structure and their properties. And we also, as I mentioned, we kind of, computed a data set about 200 composition times 6 orderings. So we use that as a holdout test set that is no one has never seen to see if the model can really, learn the different ordering and differentiate them. So this is really just show the kind of like the 2D TCA mapping of the embeddings of the model, essentially after training on this holdout test set. As I mentioned, for each composition, there are 6 different types of symmetrically equivalent ordering. That's why, for example, for this, let's say lanthanum chromium iron oxide over here, there are actually 6 different types of red stars, meaning each star corresponding to the same different ordering of the same color or the same compositions over here. But if you're looking at particularly the invariant model, actually you couldn't really see there are 6 red stars because they're literally on top of each other, meaning that the embedding learned from the model for the different ordering of the same composition are actually very, very similar. Because different ordering can have different properties. If the ML model cannot really differentiate them through the message pathing and through the embedding they learn, there's no way the model can predict the differences, right? And we also really see this also in the prediction performance over here, which I don't have space to show, unfortunately, in this particular talk. But also, if you think about you compare with the equivariant model, essentially, the 6 red stars over here, they're much, much more spatially, away from each other. Meaning now, this model, particularly model is now really starting to appreciate the differences. So embedding learned by this model on this test set data of 6 different type of symmetrically different ordering actually really to become now different in these embeddings. Just showing this is like we really need equivariant models that are really powerful to really capture learn symmetries and learning beyond scale informations to really differentiate different ordering. So just to explore explain this in relatively simple language right over here, right? So let's see if you're asking a model to really, differentiate different ordering in this 2D example over here. If we're really asking the model to focusing on scalar information, like what is the type, what is the length, distance, it's quite difficult to tell them apart, right? But if you're asking the model to really focusing on, directions, particularly the arrows over here, it's become much easier. This is overall really showing this learning ordering is a relatively challenging task in really building GNN for material structures. At the same time, if we switch to a different task, that we change the color of the atom, now we're learning the difference on composition. Because if the atom is become changed to a different color, the embedding of the atom are completely different in the beginning. So regardless, we're having an invariant model on the left or equivalent model on the right. Essentially, it's quite easy to tell them apart, no matter left or right. So overall, lots of time we're implicitly asking the model to learn 2 tasks. And one is this challenging task about ordering, and the other one is this easier task about compositions. So, whether it's a human or it's a machine learning model, if they give them 2 tasks, then naturally, likely they'll be biased towards the easy task and also, perform, badly on the difficult tasks, right? So this is really giving us warning that we need to balance the expressive power of different models in terms of composition and ordering simultaneously. So this is a really exciting topic these days. There are lots of groups these days trying to build GNNs to really predict energy and force on material structures. And this can really be a way to accelerate simulation of material. This is really one of the leaderboard. I think about it, it's kind of like the ImageNet for material that's been really very active over the past many years. There are groups and also from both university and also industry being participating. Actually, you will see a new model coming out every few weeks. They're having better metrics over here. They're all built on GNNs. But lots of the current benchmark these days are still largely focused on compositions. That's really well when you have good benchmark. Also, on atomic ordering, we do a little bit of preliminary study on these models that are top performing on the previous slides. We do find out that particularly even the state-of-the-art equivariant models, like the red one, essentially is performing better than invariant counterpart to really reproduce the trend that are really computed by quantum mechanics can largely be linked to the experimental label from the literature. So overall, I just want to give you a few more minutes about a little bit about what we did for other topics and similar lines of research. Particularly, one of the challenges these days about particularly predicting ordering is quite difficult. Is because it takes a very large structures to really predict disorder structures. So this is really because DFT or quantum chemistry, they cannot really handle a partial or let's say fracture or fractional let's say occupancy of elements. For example, if you think about this structure, essentially, if this particular lattice sites have 50%, like let's say the probability of different colors, one-to-one ratios over here, actually this is a very simple, fully random disorder structures. But in the traditional method of simulation by DFT or by quantum chemistry, they cannot really handle this partial site occupancies. But what we can really do now in GNNs, particularly, we have designed the new forms of GNNs. Particularly, we can really bring this degree of freedom of it's like 0.5, this stoichiometry, or let's say relatively ratio degree of freedom inside the GNN structures. So not only we can really directly apply to this type of structure to predict properties, we can also just do differentiable optimization, meaning we can really take the derivative of the prediction relative to the input parameter. We can really to have a more of a differentiable guided optimization directly because through this degree of freedom for optimal properties. And so this is really can go beyond the not only materials, right? So materials scientists will talk about different symmetry groups, in crystal structure, particularly in language of points group and space group. And in computer science, there are also different mathematical structures. And mathematics have different symmetry relations. And for our neighboring field of chemistry, even though they don't have crystals, have periodic lattice, but essentially they also have molecules. Molecules have very similar lines of ordering problem in the language of chirality and stereochemistry. So how do we really bridge different disciplines? This really matters. How do we really apply symmetry-aware models across disciplines? So this not only apply for, let's say, chemical disorders, right? So for example, you can have different color corresponding to different chemical elements. They can have a very, non-homogeneous distribution of chemical elements. This is what I showed previously. But also structure-wise, they can also be very different. So, for example, for crystal structures, there's always an ideal position where the atom should be, but the atom can always deviate from the positions because of the complexity of the material structures. This can be really shown experimentally. So this is also not only you can have different degree of disorder when you make the material on the spot, but also, for example, when you drive the material for chemical reactions, they can also have very, very difficult and complicated transformations for different, processes over here. This is what I really care about a lot of these days, how to really build, let's say, better AI-driven simulation method to really understand the transformation of material, about their continuous evolution during important, let's say, chemical reactions. And it's a really, really neat combination of a variety of techniques, all the way from, traditional atomic simulation techniques, all the way to, let's say, method in AI and machine learning, particularly, for example, let's say, reinforcement learning, deep learning, and also generative models. Is really requires, holistic synergies between different techniques and methods, all the way from traditional theory by governing by physics to more data-driven based approaches. And one of the things we have explored is how do we really, for example, can train active learning loops to really gradually improve ML models to really explore, let's say, low energy surface structures, trying to build this phase diagram. What is the lowest energy structures, let's say, as a function of pH and also potential different reaction conditions. We can really train efficient ML model these days through active learning. You only need to do a minimum amount of calculation by quantum mechanics just to really have very, very accurate models, can really sample a large space. So with the power of that, now we can really explore essentially on a scale of tens of thousands of different surface structures. That's why you will see essentially many, many gray lines over here. They're really corresponding to one structure being computed, also predicted by ML. So now we can really looking at very complex transformation material structure. So that's why we have a relatively, complex diagrams over here. It's really show for different X and Y, different conditions of the reactions, what is the, potentially very complicated surface transformation that will happening, really going beyond the scope or numbers of, let's say, space we can explore by traditional approach for simulation experiments. So with that, I just want to end my talk. I think I have right on time. So my group now at UB, we work a lot on how to really bridge data science and ML with material physics and also surface chemistry to build new design principles and discover materials for different applications. But one focus is really on chemical transformation, also energy technologies. We essentially work under the umbrellas of physical-driven ML, how to really build approach that incorporate theory and incorporate rigorous, exploration to really boost and accelerate a simulation of atomic modeling, and how to really work with our colleagues on the experimental side to build new data analytic method to really understand their complex data and trying to extract atomistic insight, how to really design and discover material in a more of a data accelerated approach. So with that, I just want to end my talk in the slides. So we really need that's why I'm really excited to be here, right? So this all is more on this side. We really need synergies across domains to do what we want to do and really transform the society. Thank you very much.
Thanks, Jiayu. That was a lot of stuff packed into a 25-minute talk. So any questions here? Yeah, go ahead.
Talk about ordered versus disordered materials.
Yes.
Like just glass that we have, they're not crystalline. And there's not even like, if I just blindly go into a space, I don't even know where exactly the silicon or oxygen atoms are.
Yes.
So how do you do you have a grid underlying it to try to predict material structure, or is it completely free-flowing? I'm just trying to
Yes. That's a very good question. So actually that's linked to the problem about, which I didn't cover that much, is the problem about structural disorders, right? So glass, for example, many materials, they have a defined lattice, but glass don't have it, because glass, I think we call it like glass material, or just we call it amorphous material. Essentially, they have very, random, even place where they can sit in, having a very complex structures. And right now, this is potentially where AI can come in to accelerate their modeling or simulation. Right? Traditionally, you need to build a very huge structures. essentially thousands of atoms. They're very expensive to compute by DFT, quantum mechanics, quantum chemistry. But now maybe with, for example, we can build, let's say, machine learning force field that can really predict energy and force. Much faster approach. We can really, couple with the approach of optimization structure or maybe molecular dynamics to simulate material in a much larger numbers of atoms, also larger cell, and also on a longer time scale. There are also, for example, many attempts they're trying to apply maybe also like generative models that can really generate, let's say, amorphous or disordered structures in a kind of approach, but it's still quite preliminary so far.
Thank you. Would chemistry sort of designing molecules, small molecules, be a bit more sort of appropriate for this sort of approach compared to a crystalline material?
Yeah, that's a good question. So molecule is kind of a little bit different from what I talk about because molecule don't have
all the symmetries and stuff.
Yeah. So molecule can be different because they don't have the symmetry, but molecules still have a symmetry problem. For example, the problem of chirality, essentially, they can have, left hand and right hand, right? So they're kind of essentially the same chemical elements, same kind of bonds, but they're just not exactly the same. That's the problem of chirality. Also linked to the problem of stereochemistry, essentially have the same elements, same bond, but they have different structures, different symmetry. So I think many of the insights here, for example, about ordering can potentially transform into molecule. But of course, molecule can be, it's a little bit different than material structure. For example, molecule can be shown as strings. So meaning actually there are ways to represent molecule as text strings. So many of for example, there are methods called SMILE. Essentially, you can use a text string to represent the molecule structure. That's really reasonably good. That's why, for example, you can apply more of a text-based method. For example, transformers, they can to molecule, which is a little bit more difficult to apply for material structures. But overall, there are slight differences in terms of how to represent them, about their symmetry properties, but I think many of the insights could be potentially transformable.
Thank you.
Any other questions online or here? If not, let's thank the speaker again. And
thank you.
Yeah, and please talk to your colleagues in your department and have them also sign up for talks. There are still some open slots this semester, but I think if nothing else, at least there'll be 2 faculty members that sort of get to listen to each other speak, right? But yeah, thanks everyone.